Okay, so in the previous tutorials, actually, we have seen how we can add these warping techniques, uh, and we are almost done with those stuff. So today, let's add a new feature, which is known as wall detection heuristic, right? So the wall detection heuristic means basically we have to guess whether the player or the pawn actually, or even NPC character has encountered a wall at the level, right? For example, let's say there is a wall here, right? So maybe I'll add a basic shape, maybe a cube, right? So let's say this is a wall. Right? um Maybe I can rotate it 90 degrees and place it here. Well, let's say if the player encounters this wall, we have to determine, actually we have to make a new character state. Okay, we detected the wall here, right? But we have to do it very optimized manner, right? Because as the name suggests, it's a wall detection heuristic, right? So the heuristic means we have to guess it, right? We don't know actually that is the exact answer, but based on the provided data, we can guess what is the expected result, right? That is what it meant by a heuristic. So why we are guessing it? Well, basically, the easiest way to determine whether there exists a wall or not, basically we do a simple line trace in the forward direction, right? So if this if this line trace hit a wall, basically then we can simply say, okay, there is a wall, right? But this line detection is a very expensive task. Why? Because you have to apply this line direction, line trace for each frame, right? For a specific character, right? But let's say there are hundreds of characters in your level, then each of them doing that line trace for each frame, right? So you can guess how much expensive task it is, right? For a one character, it do a line trace for each frame. Likewise, for hundreds or maybe thousand characters, they are doing those line trace until the game is played, right? It's a very expensive task, so you are basically wasting your computing resources to that specific thing, right? So we are not going to use any line tracings. Instead of that, we are using a heuristic, right? So in the heuristics, we are simply apply some mathematical terms or mathematical terminologies or mathematical calculations, and we guess whether there exists a wall or not, right? That's what this wall detection heuristic basically does. Okay, so let's see how to implement that function. So as usual, let's go to the ABP locomotion and I'll create a new function called update wall detection heuristic. Okay. So this function should be a thread safe function because we are going to add it to this blueprint thread safe update animation function call. So let's go inside that blueprint thread safe update animation, and after this update acceleration data function, let's add this update wall detection heuristic. And one more thing to mention is like make sure you are following this exact same pattern of calling the function or exact same order of calling the function, because sometimes if you messed up this order, maybe the frame updates will not happen properly, right? Because in some functions, actually, if you remember, for example, inside this update location data, actually we are doing some calculations based on the previous frame and the current frame, right? Therefore, sometimes if you change the order of execution, it may result into some weird state of calculations, right? Therefore, make sure you are following this specific order of execution, right? Okay, so we plug this update volt detection heuristic function after the update acceleration data and before the root your offset calculations, right? And then let's go inside that function and do the calculation, right? Right, so basically by using the acceleration and velocity, we can do this heuristic calculation, right? So what we basically do is we check the angle of velocity and the acceleration, and between the velocity and acceleration, if there exists a large angle, which means we can guess whether there is a wall hit or not, right? Okay, so let's get the local acceleration 2D, and I'll get its vector length xy. Let's get the local velocity 2D and its vector length as well, right? And let's check whether it is greater than maybe 0.1, and maybe the velocity actually maybe let's say less than 200, right? And if both of these conditions satisfied, then we can promote it to a variable called running, or let's say is running into O. Okay, so I'll add it to character state data, and if both of these conditions satisfies, we can determine whether we are running to a wall or not. Plus actually these are only checking the magnitude, right? The magnitude of the acceleration and magnitude of the velocity, but we have to determine the angle clamp of these two variables as well. So in order to determine the angle or direction, let's copy these two variables and normalize it, because yeah, it is safe to normalize these variables, right? Okay, so let's get the dot product. Right. So in case if you are if you are wondering what is this normalizing means, basically it convert this specific vector to a unit vector, which is 1, but it keeps the direction as it is, right? Because in the normalization we don't need to actually in this dot product we are only considering the direction, right? Therefore we don't actually need to have the exact value of these exact magnitude of these vectors. Therefore it's enough to have a unit vector with that specific pointed to that specific direction. Therefore we normalize it, right? So whatever this vector is has as a magnitude, it will become 1 once we normalized it as the maximum, right? But the direction would be preserved. Okay, so we get that dot product, and let's take in range, and as the range I'll add point -6 and 0.6, and let's add it to here. right? So the minimum dot product value would be minus 0.6, and the maximum value could be 0.6. Okay, so if the return value at the dot product within in this range, this will become true, otherwise false. Okay, then we can simply determine whether we are running into a wall or not. Okay, compile, save. So I'll add a comment, maybe check whether there is a large angle between velocity and acceleration. If true, then detect a wall, else not. Right? Okay. Right. And then what we can do? Right. So we now know whether we are running to a wall or not. Right. And maybe let's debug it and see whether the calculation works properly. So I'll use this update animation function and let's get this character state data and print string. Okay, let's play. Okay, I can see whenever we are moving freely, it print false, but whenever we encounter a wall, it quickly make it state as true, which means we encountered a wall. And actually I was unable to resolve this error. Actually it printing the print string twice. So here, as you can see, it print the previous instance as well as false. So I don't know actually how to resolve that error. In case if you know, please add a comment so I can maybe take a look, right? But anyway, you have to be focus on that the first instance or like print statements. So there we can see the state has been changed to the true, right? And if we exit from the wall, it will again become false. Okay, which means our heuristic works pretty much fine, right? And maybe what we can do is we can promote it to a new variable called whether we are in a wall or not at this update anim call by using this update anim function for each frame with the help of this is running into wall. Maybe I'll add a branch and see whether we are running into a wall or not. And if we are running into a wall, if this is false, which means we are not in the wall, right? So I'll add a new variable called in wall boolean, add it to the character state data category, and if you are not running into a wall, in wall is false. But let's have some delay until next tick. And let's do another boolean check here. And at the next tick, if the running into wall is true, then we are in the wall, right? So maybe I'll move this to here. I'll add a new sequence, and let's set a new print string, and let's test this value, right? Let's some green color, no, maybe some red color. Let's play test. Right, now you can see the in wall value has been changed. Okay, great. Now yeah, let's see what we can what sort of improvements that we can do by using these two variables, right? Let me quickly see my documentation first. Yes, so the first thing, if you remembered, at the animation graph inside the locomotion state machine, inside the cycle state update cycle layer function, I add this to do, right? Which means if we detect a wall for the update cycle animations, we can have sort of like a smaller target here, like let's say 0.5, right? Instead of having this one. So I'll remove this comment and I'll get this is running into wall and add a select node here. And let's say if we are running into a wall, then I'll have a smaller target value, right? So it will return this 0.5 instead of the full alpha, right? So it's the half of alpha that we are returning as the max interpolated value, right? And if we are not running into a wall, which means we are freely moving, then we can have the maximum alpha that it can be returned, which means it's 1, right? So the float will be interpolated to a maximum target value, which is 1, right? And the stride dropping alpha will become 1, which is the maximum alpha that it can be passed. Okay, right, now check our cycle states. Right, now you can see the foot placement is bit lower at the cycle state when the wall has been hit. Okay, right. In addition to that, actually inside the pivotal transitions, so locomotion, it's inside the pivot state machine, we have this shared transition rule wants to be pivot. So let's go one of it, right? So we have this detection, which means we are checking whether the velocity and local acceleration are opposing directions, and we have this check to determine whether we are moving to the wait, is this the correct function? Let me look at my documentation. Sorry, this is not the transition that we should look at. So I'll go back to locomotion graph. Yeah, this rule, right? So inside this rule, let's go there. So we have set of checks, right? So we are first checking whether we have a valid pivot time to be applied, and we are checking whether the velocity and the acceleration is opposing direction, pointed towards opposing directions. And then we are checking whether we have the strafing or forward facing movement mode or rotation mode. Addition to that, now we can get this is running into wall, and only if we are not running into a wall we make the pivotal transition. I'll add a new execution pin and attach it to here. Okay, let's play. Now you can see if I detect the wall and try to make the pivotal change, it doesn't playing any pivot animation, which is exactly what we want, because if we hit the wall, which means we are at a slower speed, so we don't need to specifically apply a force to get rid of that specific state. So therefore, if I try to go in the opposing direction, it doesn't play the pivot. But if you see, if I move in freely and make a pivot there, it will play the pivot animation, because we are changing the direction completely opposite, so we need to apply a force, therefore it will play that pivot animation. But if we detect a wall, right, we already reduced our speed, therefore we don't need to significantly apply a force to change the direction. Instead we have to simply go to the opposite direction, therefore it doesn't show or render a pivot any, right, which is exactly what we want. Okay, and then let's go back to the locomotion state machine, and here we have another jump from pivot sources to stop. Let's go to that function, and here also we have this function, and I think maybe later on we can make some reusable function instead of duplicating the same nodes here and there, but let's make those improvements later on once we finalize with the entire implementation, right? So here also we do set of check-ins, right, and additionally we can do that what is running into wall check. So only if we didn't encounter wall, we are jumping to the stop state. Okay, compile, save, and if I encounter wall, and yeah, it plays the stop animation. So let's go to there here. Okay, right, it also works. Right, and the next issue that I can see is if I encounter a wall, I shouldn't play this animation, right? So here you can see, even if I encounter wall, it keep playing this like cardinal direction animation with sort of a stride warping. So the stride warping been applied because the displacement speed is now 0. So you can see he's trying to place the foot in the exact same location, right? But this is quite unrealistic, right? So instead what we have to do is we have to simply stop playing any animation. We have to keep the character remain in the idle state, right, until we get away from the wall and start to freely move, right? Okay, so let's see how we can do that. So I think now we can use this in-wall function to implement that specific feature, right? So let's go jump back to the anim graph. locomotion, right? So I'll start with where? Right. So since we are keep playing this cycle animation, maybe let's start from idle source to cycle jump. But later on, actually, we have to implement the same logic for cycle and this jog sources idle as well, plus the pivot jumps. Right. But maybe I think it would be nice if we start from here or here. Here I can start. Maybe let's start from here, right? Because if we are currently remaining at the jog sources, we should go to the idle state at the very first case, right? So maybe let's start implementing this transition rule. So here we have these checks. In addition to that, I'll add a O. If we are in wall, then we are simply go to the idle state as well, right? Let's play and test. Okay, now we sort of at the idle state. You can see cycle state. Okay, now I'm at the idle state. Great. But here you can see if I try to play the start anim, it halt at that start anim because we haven't had that transition involved transition rule to those specific states. But yeah, for these jog sources, it works pretty much fine. Right. Then let's go to the idle sources to start. And there we check this stuff plus is wall in wall, not boolean. Right. And then let's copy the same thing and add the idle sources to cycle. We check this one and this one, and let's add this one. Right. So we have that idle sources to start and cycle transition as well. So let's play test. Okay. Now, even if I start with the start state, it will simply move the character to the idle state. Plus, there is no animation flickering, right? And if I start to moving only, the character will play the animation. And if I detect the wall, I will add the idle state. Okay. And then at this transition also pivot to stop. Let's go there. And we check whether we doesn't have an acceleration and whether we have a valid stop animation. And let's add a O boolean here. And if we are in wall, or if we doesn't have an acceleration, plus if we have a valid stop anim, then we jump to the stop state from pivot to stop. Okay. And finally, we have this idle aliases jump from pivot to idle aliases, which means this idle state again. So in this transition, we are checking whether we doesn't have an acceleration and whether we doesn't have a valid stop anim to be played. And let's add a new O boolean here. And I'll add this in wall here, right? So if it doesn't have an acceleration or whether we are in the wall with an invalid animation to be played as the stop, then we make a jump from pivot to idle aliases, which means we are jumped from pivot to idle state again, right? But actually this transition rule won't be applied because currently we have a valid stop animation to be played. So instead of that, it will use this transition, right? So it will go to the stop state. Okay, great. I think everything works pretty much nice. And now we can detect the wall, and if the character is trying to get away from the wall, that movement animation is being played. But here you can see like sometimes there is a small character overlapping with the mesh. So it's sort of like a collision issue. It's not actually involved with any sort of a locomotion issues. But later on we can fix those stuff, right? But for now, I think the locomotion logics works pretty much fine. Great. Right. So that's how we can apply the wall detection heuristic instead of applying any line trace features. Okay. So that's it for this tutorial, and I'll see you in the next one. Thank you.